Hello. Yep, I guess it's working. Okay, so let's start with designing data intensive applications, and I'll be going through like studying like 5 pages every day. So let's start with this. Um, let's okay, let's jump to the part one. And there are like 4 chapters. We go through the fundamental ideas to apply all data systems, whether running on a single machine or distributed across a cluster of machines. Chapter 1 introduces the terminology and approach that we are going to use throughout the book. It examines what we actually mean by words like reliability, scalability, and maintainability, and how we can try to achieve these goals. Chapter 2 compares several different data models and query languages, the most visible distinguishing factor between databases from a developer's point of view. We will see how different models are appropriate to different situations. Chapter 3 turns to internals of storage engines and looks at how databases lay out data on disk. Different storage engines are optimized for different workloads, and choosing the right one can have huge effect on performance. Chapter 4 compares various formats of data encoding, serialization, and especially examines how they fare in an environment where application requirements change, and schemas need to adapt over time. Later part 2 uses of data systems, ability, scalability, maintainability. Okay. Yeah, the internet was done so well that it people think of it as a natural resource like Pacific Ocean rather than something that was man-made. When was the last time a technology with a scale like that was so error-free? This is so true. No one knows how internet actually works, um, but they use it every day, and internet has never been down completely till now from its start. Yeah. Mm, Many applications today are data intensive as opposed to compute intensive. Raw CPU power is really a limiting factor for these applications. Bigger problems are usually the amount of data, the complexity of data, and the speed at which it is changing. A data intensive application is typically built from standard building blocks that provide commonly needed functionality. For example, many applications need to store data so that they or another application can find it again later, okay, which are the databases. And remember, the result of an expensive operation to speed up reads, basically these are caches, allows user to search data by keyword or filter it in various ways. Search indices like Elasticsearch, yeah, and send a message to another process to be handled asynchronously. This is the stream processing. Periodically crunch a large amount of accumulated data, which is a batch processing. Hmm. If that sounds painfully obvious, that's just because these data systems are such successful abstraction. We use them all the time without thinking too much. When building an application, most engineers wouldn't dream of writing a new data storage engine from scratch because databases are perfectly good tool for the job. Yeah, no one does that except for a very few people in the industry, and no one wants to build their own database and build their application from scratch. We already have good enough databases, um, but reality is not that. There are many database systems with different characteristics because different applications have different requirements. There are various approaches to caching, several ways of building search indices, and so on. When building an application, we still need to figure out which tools and which approaches are the most appropriate for the task at hand. and it can be hard to combine tools when you need to do something that a single tool cannot do alone. This book is a journey through both the principles and practicalities of data systems and how you can use them to build data intensive applications. We will explore what different tools have in common, what distinguishes them, and how they achieve their characteristics. In this chapter, we will start by exploring the fundamentals of what we are trying to achieve. Basically, reliable, scalable, and maintainable data systems. We'll clarify what those things mean, outline some ways of thinking about them, and go over the basics that we will need for later chapters. In the following chapters, we will continue layer by layer looking at different design decisions that need to be considered when working on a data intensive application. Cool. Thinking about data systems, we typically think about database, queues, caches, etc., being very different categories of tools. Although a database and a message queue have some superficial similarity, yes, both have data in them. Yeah, both store data for some time. They have very different access patterns, which means different performance characteristics, and thus very different implementations. Uh, so if we look at any whether it might be a okay, now if you look at any database, the common assumption, like how people think, is database is only for storing data, and they would think completely a message queue is completely different. But underlying is like eventually both of them store data. Eventually, if you look at any message queues, data goes in, data resides there, and data comes out of it. So the way we have to uh, we can say like message queues are also kind of a databases, but their access patterns are different, because like um, depending on the characteristics how the user wants to retrieve the data, um, or search the data, these data systems perform like perform very differently. We have we also have the search indices, like Elasticsearch, which uses Lucene search index. So this is also like there are various data strategies through which we can actually build our data systems, and we'll learn about them. Yeah. So why we should lump them all together under an umbrella term like a data systems? Yes. Many new tools of data storage and processing have emerged in research recent years. They are optimized for a variety of different use cases. They no longer nearly fit into traditional categories. For example, there are data sources that are also used as message queues. Yes, Redis is one of them. Um, and there are message queues which with database like durability guarantees, Apache Kafka. The boundaries between categories are becoming blurred. Yeah. Um, Secondly, increasingly many applications now have such demanding or wide-ranging requirements that a single tool can no longer meet all of its data processing and storage needs. Instead, the work is broken down into tasks that can be performed efficiently on a single tool, and those different tools are stitched together using application code. Yep. And for example, if you have an application managed caching layer using Memcache or similar, or a full text search server such as Elasticsearch or Solar, separate from your main database, it is normally the application's code's responsibility to keep caches and indexes in sync with the main database. So what So there are things that we need to keep our cache do to keep our caches in sync. uh, so we have our cache. Let's say this, I love to think of, whenever I think, I'll be thinking of Redis cache. So yeah, or let's say any other cache. And let's say you're managing everything through an application, so it's now the application's responsibility. uh, Everything, the responsibility is on application, so that the data from DB is in sync with the uh, with our cache. If it's not in sync, then the user, whenever the user tries to look up a data, he would get the stale data, and which is not appropriate. Uh, but depends on the application whether the user is fine with the stale data or not. It's completely the application requirements, and how we want the system to work. There are so many trade-offs which needs to be made, and we will see what kind of trade-offs, and how these systems, like how we are going to build these systems. It is going to keep those caches in. Figure 1 gives a glimpse of what these may look. We will go detail chapter step. We have a nice, so a user makes a request to the API. It will come to the client code. Now the client code will read request from the in-memory cache, not an external cache. If it's Now if there's a cache miss, then it will read from the primary database, and primary database will return it to the application code. uh, and now it's the application code that needs to invalidate the cache and update it, or update it, yeah. And the application code is also responsible for make any updates to our search index, so that any search request can be searched from our search indices. And and any asynchronous tasks are sent into message queue, which is handled by another application code. uh, this is a complete asynchronous flow. But as you can see, like application code is doing a lot of work here, which is like uh, updating the cache, or updating our text indices. Yeah. When you combine several tools in order to provide a service, the services interface or application programming interface usually hides those implementation details from clients. Now we have essentially created a new special purpose data system for smaller general purpose components. Your composite data system may provide certain guarantees. Example, that the cache will be correctly invalidated or updated on writes, so that the outside clients see consistent results. Yeah, this is what we talked about. Basically, the cache needs to be invalidated or updated, so that the client sees the correct results. Uh, but this is something we'll discuss. I think we'll discuss more later. It's like how, for there are systems where the users are fine with not seeing the latest data, and we'll look into those kind of systems. You are now not only an application developer, but also a data systems engineer. Yeah, makes sense. You're designing a data system or service. A lot of tricky questions, right? How do you ensure that data remains correct and complete, even when things go wrong internally? uh, yeah, let's say something goes wrong, our code application server fails or something. How do you provide consistently good performance to the clients even when parts of your systems are degraded? How do you scale to handle an increase in load. What does a good API for the service look like? There are many factors that may influence the design of a data system, including skills and experience of the people involved, legacy system dependencies, the time scale for delivery, your organization's tolerance for different kinds of risk, regulatory constraints, etc. Those factors depend very much on the situation. Okay. In this book, we focus on three concerns that are important in most software systems: reliability, the system should continue to work correctly, perform the correct function at the desired level of performance, even in the face of adversity, hardware or software faults, even human error. Um, Anything uh, wrong that can happen will happen, but even though our system should work correctly. Let's say one of our like our database crashes, but our system still should be able to work correctly. Maybe we should have backups. Such kind of things we'll discuss in reliability, how to make our systems reliable. And scalability. As the system grows in data volume, traffic volume, or complexity, there should be a reasonable way of dealing with the growth. Let's say your system was great at handling 10 users. Now the number of users grew rapidly and now you have 1 million users. Now how is your system, like how scalable is your system? How can it handle uh, a variable number of requests, like traffic? There can be traffic spikes. There's a huge change in data volume. Previously used to get only 500 write requests, let's say. Now we are getting a 5 million. Yeah. And maintainability. Over the time, many different people will work on the system. Yeah. Engineering and operations, both maintaining current behavior and adapting the system to new use cases. And they should be all be able to work on productively. See maintainability. Yeah. Okay. These words are often cast around without a clear understanding of what they mean. In the interest of thoughtful engineering, we will spend the rest of this chapter exploring ways of thinking about reliability, scalability, and maintainability. Then, in the following chapters, we will look at various techniques, architectures, and algorithms that are used in order to achieve these goals. Okay, we'll stop here and we'll continue the rest tomorrow.